we're in chapter 9. There are only 2 sections to chapter 9. So our goal is to get that finished this week, which we will. And on Monday, we'll review for the final. And on Sunday, the 6th, is when all the homework should be due, right? So keep that deadline in your head. Sunday the 6th, get all the homework finished, right? All the assignments done. And then we'll be on to our final. So what's the session? Well, we're going to do, essentially chapter 9 is to do with a thing called linear regression, which is basically taking data and trying to fit a decent straight line through it, if it's feasible to do so. So let's get started on what's called a scatter diagram. So imagine that I collected some data, and along the horizontal, we had age, these are children, and vertically we had their height. And so you have, I don't know, 1-year-olds, 2-year-olds, 3-year-olds, 4, 5. Yeah, that seems reasonable. And well, for babies, it's, I guess, their length rather than their height, but you can still measure it, right? And you have a height thing. I'm not going to put the numbers in because I'd guess I'm wrong. But you collect data on number of children, and you have a 2-year-old that's this height, another, well, almost 2-year-olds that height, and a 1-year-old and a thing here. And essentially what you get is called a scatter diagram. And it might look something like that. Can you imagine that might be what your data looks like? So let's introduce you to some terminology. The age here is called the explanatory variable. And basically the x-axis is the explanatory variable. And the y-axis, oops, I'll do it in red. And the y-axis is called the response variable. So if you have a question and it's talking about the response variable or the explanatory variable, you kind of now know what they're talking about. Great? Just terminology. Now, when you look at this set of data, we're going to try and introduce terms that we use to describe it in words. One of the terms I'm going to use is that this data is linear. What that means is, would you agree, although it's not a perfect straight line, doesn't it fit in a general sort of a way, a straight line? Would you agree? And if I try to draw that straight line, it'd probably be that line there. Yeah, maybe put a few dots up here to make it more likely, right? Linear. We also talk about, so that's basically the shape. And we're mostly interested in linear, but can you imagine there could be data that's curved? Can you imagine the data look like a happy face or a snake, right? I guess we describe that data as curved in some way. And then we talk about the strength. What we're talking about here is the strength of the relationship, which is how good a fit is the data to being a straight line? Well, we use terms like strong, moderate, weak, and none. So when we talk about what kind of linear relationship is there, it could be a strong relationship, a moderate, a weak, or none. And it's a little bit subjective, but let me try and draw what they might look like. Right? So without putting axes on them, because that would take two, names of axes, can you imagine that the data look like that. It's very close, right? Everybody's almost in a perfect straight line. That's what strong would look like. Now, if you're looking at none, can you imagine the data? Would you agree there's no obvious straight line in that very badly drawn scatter plot, right? That scatter diagram. That's what none would look like. So we've got two more guys. Oops, change color scheme. We're going to do moderate. And then we're going to do weak. So weak would be, yes, it's linear. But would you agree it's kind of vaguely linear? There's lots of places where that line could go. And moderate is somewhere between this and this. So I'm going to put in some relatively strong ones and then kind of weaken it a little bit. Right, do you get the feel for, and it's, as I said, it's a little bit subjective. So if you're not 100% sure, you can say things like moderate to weak or moderate to strong, you know, where you're sitting on the fence, you're not quite sure if you want to go 100% with one of those terms. The way I do it, and it's not a scientific way, is I think of sausages. And you think, what's he talking about? If you draw a sausage round the data, can you see that the fatter the sausage is, the weaker it is? That's what I mean by the sausage test. Now, it's not a real test. You won't see it in a textbook, but it helps me. Do you get the gist of what I mean when I say the sausage test then? So if I use that term sometime today, I'm talking about how skinny the sausage is, right? And if it's a really tight, skinny sausage, doesn't that mean it's a strong? And if it's a big, fat, kind of, a lot of meat in it kind of sausage, then it's weak. And I don't think I'd even call it a sausage. If I tried to draw some around it, would you agree it'd just be a big blob? I think the none is the easiest one to recognize. I don't think you need the sausage test on that. Are we comfortable with the terminology then when we talk about strength? Okay, so you can have linear, which is the ones that we're concentrating on. You can talk about how strong that linear relationship is. So you might say it's a moderate linear relationship or a weak linear relationship. Now there is another term, which is, oops, I guess I should put it over here because that's where my little list is. And a line can have a positive or a negative direction to it. You sometimes use positive correlation and negative correlation. That's just another word for the same thing. So can you imagine data that look like that?
One more row.
Say that again? Not me. Okay. And can you imagine some data that look like that? Those very there. This is positive, and this is negative. The way I think about that is, can you imagine the slope of the line? Won't that be a positive slope, and won't this be a negative slope? We very often say positive correlation and negative correlation. Are we so far so good? Right, getting this terminology of how you describe. So I'm going to put up a pretend set of data. I don't know, let's try green just to be different. And let's say along the bottom it is the weight of something, and vertically it's how much it would cost you to buy it. I know, buying apples from various shops, right? How much, what the weight of the apples was, how much they cost. Right, this fella here, which one of them is the explanatory variable?
Weight.
And response variable? Cost. Great. Would you agree this is linear? Great. Which one of the strength terms do you think would be most appropriate to this particular set of data?
Moderate.
Moderate. Would some of you go strong? Some of you might go strong. So if you wanted to cover your butt, wouldn't you say moderately strong? You see how you can kind of merge the two together. If you're not 100% sure, if you are 100% sure, you know, stick to your guns in. That would work. Now, a guy I've not done yet, but I will. Imagine there's a dot away over there, sitting as his lonesome. He's clearly not part of the usual data pattern, right? He's the odd one out. What do you think we call guys that look like him?
Outlier.
Yes. Doesn't it make kind of sense, you know, as a name, what that guy would be? Now, this particular outlier doesn't look like anything in the data. Can you imagine there's a guy up here who's in the same straight line, but you notice that there's a big gap with nothing there, and then a data point? He also counts as an outlier. So an outlier is any data point that is not in the usual sausage, right? Would you say that's where the sausage lives? Do you notice that those 2 points are not in the sausage and there's clearly distinct space between them, right? Now, as you are thinking about who is an outlier, in this case, I've got two. I'm going to put little X's. And next to the X's, I'm calling them 1, 2, 3, and 4, because it is a little bit subjective after a while. If there was a data point at 4, do you think he's separate enough to still be an outlier? I think most of us would agree it's an outlier. What about 1? Do you think that's far enough away, or is it kind of generally still in the sausage if I made the sausage a little bit different shape? So do you see that you're going to have to make a judgment call? It's kind of easy when you get a guy out here and a guy out here, but can you imagine as I slide towards the sausage, won't you finally get to a point where some of you are saying, you know, you could make the sausage just a little bit fatter and you would get that guy, right? And it wouldn't really be that big an effort. Are we good? Terminology? Let's talk a little bit about, oh, I forgot a term. Positive or negative correlation.
Positive.
Yes, positive. So, I'm going to show you 2 examples of scatter diagrams. Along this one, I'm going to do the, actually, I'm going to do age and height. And we collected pretend data on the ages of some children, and we plotted it against their height. And the data looked like that. So there's my sausage. Linear, positive, no outliers, moderate to strong, depends how you feel about it. Age would be, in this case, the explanatory variable. Height would be the response variable. Now, can you imagine that we try to fit a straight line through that data, one straight line? My guesstimate is this blue line I've just drawn. This line is sometimes called, it's got lots of names, unfortunately. It's called the line of best fit. That's one of its names. I kind of like that name. But you'll also find it called least squares line. Don't like that name so much, but it's sometimes called that. So this line of best fit is the best fitting straight line through the data. Now, right now, you might think, well, okay, I can, maybe if I put an extra dot in, I'll convince myself. That line's pretty good. It fits most of the data points, or at least it's close to them. Would you agree that this pen would be a very horrible line for the line of best fit? And that would be just wrong. But can you imagine that there might, if I gave you the same data, right? I printed it out and I sent it to you with all the dots, and I gave you a ruler and I said, draw your line of best fit. It wouldn't surprise you that everybody might draw a slightly different line. It might be a little bit higher. It might slope a little bit differently, right? There's a lot of wiggle room if you do it by hand. The good news is that there is one line that is the best fitting straight line. It's unique. And there's a multiple set of calculations that you have to do to get it. Thankfully, SALT does those for us. And it will give you the equation of that line. And the equation of that line might look something like, well, we'll use H for height, okay? And A for age. It might say, in fact, I'll put age in. That's probably a better, right? And some textbooks put a funny little hat above it, you know, the little caret symbol. You read this out as the predicted height is equal to 15 plus 3 times the age of that child. So if this was, yes.
Is that like a what do they call it? The slope intercept form or something?
It is. It's exactly that. It's called, in algebra, it's called the slope intercept form. You're right.
So it's the same idea.
Yeah, instead of y's and x's, we have
Right.
variables age and height, but it's exactly the same idea. Yes. Now, when you look at this predicted height formula, what that says is, if you put a 10-year-old child in here, it'd be 15 plus 3 lots of 10, predicted height 45 inches, right? That kind of thing. If you put a 2-year-old in here, it'd be 15 plus 3 lots of 2, it'd be 21 inch tall. What you've got here is a formula. We call formulas models in mathematics. So we have a formula, a model, that you can use to predict the height. It's kind of useful, isn't it? So you collect a lot of data, and then if you've got a good data set, right, a nice tight straight line, really strong correlation, then this prediction will be really good. And if you've got horrible data, right, it's spread all over the place, you can still put a line through it, but can you imagine that in those situations, your predicted value might be, it's a bit of a guess, really. I'm not that confident in it, right? So tight, skinny sausage, confident on the prediction. Big fat sausage, not really sure if it's a good predictor or not. It might be lucky, it might not. Now, in this particular situation, we would say, and I think with a lot of justification, wouldn't a height and age be connected? Would you agree the older a typical child is, the taller that child would be? Would that make sense? There's a distinct positive correlation between age and height. And so we would write that down as a positive correlation. Think of the word correlation as meaning straight line, right? So there's a positive correlation between age and height. Now I'm going to show you a nonsense one, but only nonsense in the sense that the conclusions are clearly stupid, right? So I'm going to have along the bottom shoe size, and vertically reading age. So you got some kids, right? Some children. And you measured two things about them. You found out what their shoe size was, and you found out what their reading age was. So you know you can do tests where you're reading at a 9-year-old age, or you're reading at a typical 6-year-old, right? That kind of test, right? There, I'm going to just do a little mute here because I'm getting some background sound. So can you imagine that situation, right? And this is the data that I got. Positive, linear, strong or strong to moderate. If you do your little sausage around it, right, you agree it's a pretty tight sausage. Can you imagine the line going through it? Looks something like that. Now, when you say there's a positive correlation between age and height, a lot of people think that means, because it does in most situations, that your age is why you're the height you are. Would you agree that 12-year-olds tend to be taller than 4-year-olds? And the older you get, up to about 17 or so, the taller you will be. And that is quite sensible. What you're saying is age causes the height that you're in, right? There's a direct connection between each. Now, according to this, then, shoe size and your reading age are positive correlation as well. You agree? So we would say there's a positive correlation between shoe size and height. Now, that does not mean that your shoe size causes, oh, I'm saying height, apologies, reading age. That does not mean that your shoe size affects you directly as your reading age. There's a positive correlation, strong positive correlation. That just means that it's linear, right? It doesn't mean that shoe size causes your reading age. Now, if that was true, if you had a child who was really bad at reading, right? You had a 5-year-old and they could hardly read at all. If this was true, couldn't there be a really weird operation where they go in and break your child's feet and stretch their feet so they're 4 shoe sizes bigger? And the next day they go to school, they're going to be reading at a 10-year-old. Because if that was true, wouldn't that be how you would solve the problem? What we have here is a situation, well, that involves a thing called a lurking variable. A lurking variable is the real reason for this connection. And typically what that does is that the lurking variable is very strongly connected to the shoe size. What do you think the lurking variable for the children is in this case? What makes shoe size in children get bigger? What changes in a child that makes a shoes age? I bet you if I recollected the data, but this time I took the age of a child and measured against their reading age, can you see that would be pretty much the same relationship, wouldn't it? 10-year-olds tend to read like 10-year-olds and 5-year-olds tend to read like 5-year-olds, right? And so working variables are the bane of existence, because when you get medical information given to you and they're looking at what people do along the x-axis and what the response is along the y, you can come up with correlations, and then they make the leap to, and that means that this causes that. Make ones up because I can't think of any decent ones right now. Suppose you measured the amount of fat intake that a person, various people took, and you measured that against their blood pressure. And you would find that the more fat they ate, the higher their blood pressure was. And you might think, that's it. Eating fat is the main cause for people's blood pressure. Well, it's not that. Don't people who eat a lot of fat probably eat a lot of other stuff? And it's actually your total weight that's affecting your blood pressure, right? People who are really overweight will have high blood pressure because their poor body's got a lot of body to pump the blood around, and you know the heart doesn't really get that bigger, right? So it doesn't compensate. So that would be a lurking variable situation. Here is a classic one which they use in quite a few textbooks. Not this one, strangely enough. This is going to have a lurking variable in it, and I want you to try and figure out what this lurking variable is. Oh, what's the term? It's life expectancy. Well, I should have thought that through a bit better. 0, 1, 2, 3, 4. The average number of televisions per household in a country. So each one of these dots is a country. And you have life expectancy. So 50, 60, 70, 80. I guess there might be some places in the world with 90. If you plot a country's average number of TVs per household and the life expectancy, right? What's the average age a person in that country lives to, right? Life expectancy. You get a positive linear correlation that is actually pretty strong. Does that mean owning TVs make you live longer? Right? There's a positive, strong positive correlation between the number of TVs and life expectancy. What would you think might be a plausible lurking variable for this story?
Income?
Yeah, that's the one I would pick. Would you agree that countries that are rich, right, a lot of income, right, the average income for people in these countries is high? Don't they tend to have lots more TVs than places who are not rich countries, right?
Could we also do like level of activity?
You could factor that in, but I get you. If you've got lots of TV, there's a lot more couch potatoes, so you don't have activity. Yeah, I could understand that one. I'll go for the income one, but yours is fine. I like that one too. You know, if you've got a lot of income, what else do you tend to have? Well, lots of TVs, right? We've covered that. But don't you probably have access to lots of better healthcare, which probably will keep you alive longer? And don't you probably live in a better house than some corrugated iron place, right? Don't you have better sanitation, better sewerage system, better food access, better medical access. You see all those factors that go with rich countries, and you get less access when you're in a poor country. Can you see how wealth might be, or income as you're calling it, would be a pretty strong reason for this particular connection? And so when you get some questions that talk about lurking variable, I think the box says various answers, which means that levels of exercise would work. Income certainly would work. Can't think of another one, but you might come up with one later on. So there's no one right answer to the lurking variable. We could, of course, recollect the data and have average income against life expectancy and see what that looks like. If the dots are all over the place, then that means income had nothing to do with it. If the data is very tight and linear, then it might mean that we're at least close to the right variable, if not finding the right reason for the relationship. It's basically quite a long intro, but hopefully we got a lot of the gist of it. I think it's time to start looking at what do the homework questions look like, right? So if you hold on, any questions before I move on?
I have a question, but it's about chapter 8.5.
Can we do that at the end, just hang about, Bethany?
Yes, perfect.
That'll work perfect. Anybody else got homework questions like Bethany? When I say goodbye, don't go away. Just hang about and we'll do some of those for you. And let's leave this fella, go out and go in, and it should be screen 2. And can I make this a little bit bigger? Bump, bump. Okay. When drawing a scatter diagram, along which axis is the explanatory variable and which one is the response? Haven't we already told you that, right? So you'll be able to hopefully pick that one. Suppose two variables are positively correlated, right? So your scatter diagram is positively straight line. Does the response variable increase or decrease as the explanatory variable increases? So as x gets bigger, what happens to y? If it's positive. As x gets bigger, what happens to y?
Gets bigger.
Gets bigger. So you pick the answer in there that is what you just said. There's a negative version. Oh, I never talked about that. I'm glad I did this. I'm going to nip back and show you a little bit more detail on one of my earlier pictures. Because I forgot this section, had this bit in it. There is a number, a very special number called the correlation coefficient. The correlation coefficient, little r. And little r takes values between 1 and -1. In this case, it's probably about 0.9. If it was exactly 1, can you imagine you get a perfect straight line? So an r equals 1 is a whole set of dots all on one single straight line. That's like perfection. But that's not perfect, right? So, but it's good, so it's 0.9. And this guy here might be 0.7. Right? Positive, but not quite as good. This guy is about 0.5. And this guy is about 0. Now, it won't actually probably ever be 0. It's more likely when you calculate this R, or at least when the calculator does it for you, or the software does it for you, you'll probably get an R value like 0.1 or -0.1. So what do negatives look like? Can you imagine data pointing down the way? Oh, I should just do my sausage. Why don't I do that? That's much better. Skinny sausage going down the way. Fatter sausage going down the way. Oh, even fatter sausage going down the way. And a whole lot of nothingness. Now that would be negative 0.9, negative 0.5, oh sorry, 7, and negative 0.5. So can you imagine that we now have a single number called R that kind of puts a number on the strength? So if I said I have a scatter diagram and the R value is 0.2, in your mind, do you see a kind of blob of not much happening? If I said it's an R value of 0.8, do you see it's pretty good sausage? It's very linear. And also, can you tell, because I said positive 0.8, that it's a positive line, right? It's going up the way. And that is positive correlation. And so that was a bunch of questions I forgot. I can now return. And we'll look at those questions again. Hopefully, they'll now make more sense. If you're near -1, which one of those 5 dots, 1, 2, 3, 4, or 5, which one of them do you think you're looking at? Near -1, like a negative 0.9 kind of number, right? Dot 1, 2, 3, 4, or dot 5?
5.
I agree. Would you agree it's strong because it's almost at -1 and it's negative? If it's near 0, how about weak or no linear? And if it's near 1, how about strong but positive? That makes sense? That was nice, easy, because you only pick a dot. Here are 3 scatter plots. And then there's another 3 after, but let's look at question 5 first. Can I get a little bit more size on that? Because I'm not sure what size your screens are. Right, this is A. Now, list is the choices. No, high, moderate, or low. Which one of those 3 best fits A, in your opinion?
Moderate or low.
I would agree. Would you see this one here? Would you agree? I know there's a couple of kinks, but would you agree that's probably strong? Which they're calling high. And what about this? Well, it might be a nice curve, but would you agree a nice curve is the worst version of linear you could ever get? So that technically counts as a no. Correlation is linear correlation, right? It's straight line data. If the data ain't straight line, as nice as it might look, it doesn't have any linear correlation, right? It doesn't have any straight line part. Single straight line, I guess you could say there's 3 straight lines, but it doesn't count. Okay, here's 3 more. What do you think B should be? And here's the choices.
High.
I would go high. I guess they could have told us linear and negative, but they never gave me those, so I'm just picking the strength. I think everybody's going to agree with C. Right? You all agree it's no, it's got none. Right. Right, here's one of these correlation causation. And there's a phrase that we use in statistics that sounds a bit of a mouthful, but it's a good phrase. Correlation does not mean causation. correlation does not mean causation. It means just because you've got a nice fitting straight line doesn't mean the X is causing Y. You remember the one we did with the TVs? That would be an example of that. Correlation is not causation. So over the past few years, there has been a strong positive correlation between the annual consumption of diet sodas and the number of traffic accidents. So the more Coca-Cola we drink, the more traffic accidents there has been. Do you think the increasing consumption of diet soda caused those traffic accidents? Well, there is the answer I'm picking. No, I don't think it did cause it. A strong correlation does not imply causation, right? That's that phrase I used, right? Correlation does not imply it. So now we need to think of what on earth could a lurking variable be? And there are lots of possibilities here, right? So why should the increase in the diet soda and traffic accidents, what on earth could be happening here? And remember, there's no really right answer here. There could be lots of right answers. I've got one. I'm not 100%
Maybe driving distracted.
Well, okay, like Coca-Cola, like phones and everything else, they cause distractions and cause accidents. Okay. I'm not saying that's wrong. That's as good an answer as mine, probably better than mine. Any others?
Maybe a lot of the people who drink soda, there's a lot of younger people, and maybe there's a lot of younger drivers out.
Ah, so that's like a double lurking. More soda because younger drivers cause more accidents. Yeah, see, I'm not giving mine now because I like both those answers better than mine. So, but you get the gist of it. You just put in something that makes sense, at least to you. And I know you're not used to math questions not being x equals 10, but trust me, if it was a sensible answer, it's fine. I don't think the software actually is clever enough to read it. So it's really for your benefit that you're writing these things in. Well, how about this one? Over the last 10 years, there's a strong positive correlation between teachers' salaries and the cost of prescription drugs. That's another correlation is not causation one. So I pick that dot. Now you got to tell me, what kind of lurking variable could cause me to get paid more and drug prices to go up? And I know it's not with me taking drugs, because I don't, at least not illegal ones. I take prescription drugs. Right, give me a good one. I got one. I think it's a good one this time. So I'm willing to share this one.
Inflation.
Yeah, that's mine. You know, in 10 years, doesn't the price of everything go up? I mean, if you went back and found an old advert for, I don't know, £1 a steak, right? A T-bone steak or something. I bet you in the last 10 years, it's went up, whatever it is, 12, 20%. That's what I would go for. I would say inflation. And then when you say why, you might say something like, over the 10-year period, the price of everything has gone up, including drugs. And of course, wages have gone up. Most people's wages have gone up in the last 10 years, right? We'll let you read that one on your own. There's another one that you're on. And now we're on to a totally different guy. Can you remember, I think it was week 1 or week 2, we had this annoying guy. Remember plotting dots and having problems with trying to make it work? Okay, you're going to have some dots to plot and you're going to have to make them work. So we are going to plot these sets of data. They haven't even bothered to give them names, and that's fine. But if you want to know what X is the age of a pony, and y is its weight, right? So they've got various, or maybe the same pony, whatever. So 3 and 60. So hit the dot and pick where you think 3 and 60 is and go click. And then go over here and hit it and change it to what it should have been. Right, so that's how you get the accuracy. Right, now the next dot is going to be 6 at 95. 6 at 95 there. Go to point 2. Oh, got that one right. You see how I'm doing this now? Just to remind you. But this time it's the dot one. Don't use that guy or that guy. That's for lines. This is a little bit easier. Just pick the dot one, right? The next one's 12 and 140. So 12 and 140 is about there. And you know how pernickety this is, so you better make sure that these are checked and fixed if they're a little bit out. 17, 164, 17's about here. 164's kind of there. So it's not too far away. And the last one's 23 and 179. So 23 is about here, and 179 is about here. That's miles off. 23, but I got the 179. Right, we are looking good, I guess. Now, make a scar diagram. Done. Would you say this is low, moderate, or strong? Now, I know there's not a lot of dots there, but can you imagine the sausage? Low, moderate, or strong? What's your gut feeling?
Moderate.
Yeah, that's my gut feeling. Now, some of you might think it's strong, and I'm not saying you're wrong, but you know what will happen? You get 3 shots, so if it ain't the one, you change it to the other one, right? So it's not like it's a big deal. This one there is no argument about. Would you agree this is positive? How do you know the sausage is pointing uphill, right? Now it goes on here and says use your calculator to compute R and then some other stuff. Now that's not what we're going to do. There is a way to do it in your calculator, but I think that's a lot of work. So we are going to find, remember that magic number, R equals 0.9, R equals 1 was perfect, that number? That's the guy we're going to find, but we're going to do it using SALT, which is so much easier, right? So I'll click on SALT, and you are now looking at this guy. And the fella that we're going to use is called regression. And it says select a variable. And the first one was age, and the second variable was weight. And I'll take that out. Yeah, well, that's kind of what my picture looked like, sort of. Now, the guy that we're looking for is kind of cryptic. He's called correlation. Now, they should have called him little r, but I can't help that. Can you see the number? 0.969. So I'm going to revamp one of my answers now. 0.969. And I am going to revamp this answer to strong. Would you agree that 0.969, would you agree that is darn close to perfect, which is 1? Do you see how our visual ability isn't as good as our number ability? See, if that R was 0.8, I'd be going moderate again, wouldn't I? Not that I think it could happen, but can you imagine that R was 0.6, wouldn't I be going weak? But a number I can, I can have a range of numbers, right? In this range it's strong, in this range it's moderate, in this range it's weak, and in this range here it's nothing at all, that kind of thing. And there'll be a little bit of wiggle room in the numbers, but at least I've got something to work with. Now, this phrase here is a little bit cryptic, so let's try and make it English. Can you imagine X being this direction, right? So X is the age and Y is the weight. So as the age increases from 3 to 23 months, does the value of R, which is 0.969, imply that the height should tend to increase or decrease? Well, if I just look at my picture, it's pretty obvious. Age, height. Age increases, height increases. And since R is a positive number, isn't that also an indication that it increases? Positive R values only happen when you go uphill, right? And which one of these puts that together? And I believe it's that sentence there. Right? So given our value of R, Y should tend to increase as X increases, right? So for positive R values, that statement is true. If it was a negative R value, you can imagine negative 0.8 or something, then as X increases, won't Y decrease because it's going downhill? Are we good? Okay.
How did you
Yes.
find R again?
Say that again.
How did you find R again?
Oh, I went and I hit use salt. I'm going to go out of this so I can go back in. Hit regression. Select the variable. X was the age and Y was the height. That was in the story. There's a little scatter plot that we don't need. And the guy that we are looking for is called correlation. Do you see it's hidden there?
Okay.
Right. Are we good? Now, there's lots of other things here which are really interesting, most of which you'll never use. But that number right next to it is quite interesting. Do you see it's called, strangely enough, it's called R squared with a capital R. Correlation coefficient uses a little r. But do you know this guy here is that guy squared? So if you multiply that number by itself. And what this number does, it's called the coefficient of determination. That's its fancy name. That number, if you turn it into percentage, kind of tells you how good a fit the data is. It's saying 93.9% fit. So can you imagine you're like, perfect's 100% fit, right? But 93.9%. The jargon is 93.9% of the variation is accounted for by the model. That's just the statistician way of making that sound clever. It just means, A, it's a really good fit. Do you know an R squared of 20% would be horrible? It's a 20% fit. Turn that on its head. Isn't that 80% of them don't fit? They're totally somewhere else. Right, a 90+% fit, isn't that a pretty good fit? Can you imagine that would be like a strong linear relationship? Okay. Did that answer your question for you, Brittany?
Yes, I just accidentally clicked the R, the one that said R.
Yeah, the one that just said correlation above it was the R value. So the one to the left of R squared is called correlation, and that's the number that goes, well, I've lost the damn thing. That's the number that goes here. Compute R. Now, if SALT was being nice, shouldn't they have just stuck a little R above that number to make it easier to find it? I mean, they could have, but they just didn't. Is it okay to move on? We're comfortable with what we're doing? We're going to do more practice at using SALT. So if you're wondering what's coming next, it's pretty much the same thing. Yes.
That is a bit off topic, but
I'll
had
go for it.
there
Yeah,
was something the other week we left off on 8.5, and I just wanted to ask before I forgot, and it wasn't working the last few questions.
I got that to work fine the second time.
Oh, you did?
I did. And I don't know what I did differently because I did the same thing and it worked perfectly fine.
Because mine's still having problems.
I have got a video of me doing those last few questions, which I only put on my Tuesday class because it was them I did it with. I'll get that video and stick it on your class's thing, and you can look at that video and just see what I did. And maybe if
Okay.
you can follow that, I'll take you through it. I can certainly do one after class if you want me to go through it right then, save you waiting. That
All
may
right,
help.
thank you.
Okay. Okay. Are we getting the gist of what I'm going to do here? Because it's pretty much the same as before. Here is a set of data. I'm going to pretend this time that I'm doing it right for speed. 3,40, good grief, would be about here. Oh, hit the dot. 3,40 is about here. 7,35 is about here. 1530 3726 and 7220. Now I would just go in and fix these, but can you pretend I fixed them and it was good, right? Now, for this set of data, actually, I don't know if it's my brain or yours. Can you see a curve there rather than a straight line? Do you think that, I mean, that data is not a great fit, would you agree? To a straight line at least. So I'm going to go low and negative because it is pointing down the way. Do you agree it's getting less? And now I want the R, which is use salt. Pick regression. That guy goes first. That guy goes second. And the fella we want is, I was amazed. That number is a lot better than my brain told me. Would you agree that's negative 0.9 is actually a pretty decent number? So go figure, I'll copy that. And then put the answer there. And this time it's decreasing. So as X increases, Y should decrease. This one is measuring barometric pressure against maximum wind speed. This one here is the magnitude of an earthquake and the depth below the surface. Okay, I could try that one. 2.9, which is about here, matches with 5. Then go over here and do, that's a weird set of zeros. Good grief. Did you see how many zeros that had? 2.9 goes to 5.0. Hope I don't have to do that again. Right, got the first one. Second point is going to be 4.1, 9.7. 4.1. Okay, I'll keep that one. 3.3, 11.2. Okay, I'm not going to fix these. 4.510. 2.67.9. 3.2, 3.9. And 3.4, 5.0. Well, not the prettiest one in the world, but that's what the data looks like. Okay. Any ideas? Does that set of data have any linear shape to it that you can see? Looks like a column of data, doesn't it? It just looks like it doesn't have any shape to it. Let's find out what SALT says. Since there's so few data points, it'll probably be a little bit inflated because of that. And that just means it'll be bigger than it probably would be with more data. Yeah, it's positive allegedly, but very weak. So the only reason I couldn't see it wasn't this crushed into a corner? Maybe if I did a different scale, I might see it a little bit better. 16, same basic question. Oh, some a little bit different to finish. The initial visual impact of scatter diagrams depends on the scale. That one we just did a few moments ago was a good example of why if you crush your data or use poor scales, it's hard to see the underlying pattern. So here is a set of data. And it says making a scatter diagram using the same scale on both the X and Y. So in other words, if you're doing one box is one, you go 1, 2, 3, 4, 5, 6, and up the way, 1, 2, 3, 4, 5, 6. Now I should be able to, if I shrink this down, if I can actually shrink it down. There we go. As I try to look at the data, that one's out just because this vertical scale is not the same as the horizontal. If I look at this one, 1, 1, 2, 4. Unless my eyesight's really bad, would you agree that that dot is not at the right place? So I'm throwing that one out because of that. Right, let's do 2, 4, that's good. Let's do 2, 4, that is good. Different scale, not using it. That basically means it was that one by a process of the scales weren't the same and that dot was in the wrong place. And there's another one. And wow. I thought there was a second question, but I was wrong. Well, let's leave that and return back to here. Okay. So what we should have got from today, the vocabulary, you know, with the strong, moderate, weak, the R value, how to use SALT to find the R value, and how to use the R value to make a prediction that as X gets bigger, does Y get bigger or does Y get smaller? Oh, and we also looked for lurking variables, right? Which is, it's not always the case, right? Correlation does not mean causation, right? There could be things like lurking variables, which are the real reason for the connection between the two things. Right, if I haven't asked you, and I don't think I have yet, will you all say hi so that you can get your attendance for today? And I'm going to hang about at the end because I have some people with some questions. And if you want to stay behind just to hear what their questions are and see what the answers are, then feel free to do so. Okay, that's it. Bye-bye, those who are leaving. Bye-bye, Ethan. Okay, we got a lot more. That's cool. I'll wait a few seconds. Right, we've got a lot more people behind. So who was the first person? Somebody asked us. Bethany, I think it was you. Or
Yeah,
was
that
it
was,
Brittany? Who was first? Bethany? Brittany?
it was me, Bethany.
Okay. Right, what you got for me? What's the question?
Okay, so last time that I was in class, we were going over 8.5 and you said to do up to number 8.
Right.
The U1 and U2.
Right, but I've managed to get the others to work. That's connected to the same question that I think Joshua was having a problem with. So why don't
Yeah.
I go in and do some of those, at least one anyway, and if you need another one, I'll do two, to show you what's going on, okay?
Sounds good. Thank you.
Right. Not a problem. So give me a few seconds to load up 8.5. And can you remind me what was the first question in the ones you're not to have done?
You said to do up to number 8. So I
So anything after 9 is what I should be looking at, right? So that's like the last 7 questions, right? Let's check that. Yes, Joshua.
I thought we got up to, wait, sorry, which one did she say? 8? I thought we
Yeah.
got up to like 11 in the
Yeah,
class. And I thought it was,
yeah, 9 and 10 are fine. I'll show you 9 and 10 while we're here, and then
it
we'll
was
go
like
into
12
the,
and on that was not working for me at least.
okay. So that'll be a good place for us to go. Are you looking? You probably aren't yet, so let me fix it. Are you now looking at the homework? 8.5. Right. Okay. So these questions here, 9 and 10, are really just alternate and null hypothesis. So we kind of did cover them. So, but we'll do it anyway. When conducting a test for the difference between two independent populations, what alternate hypothesis would indicate the mean of x2 is smaller than the mean of x1? So you're just looking for, well, to say that x2 is smaller than x1, another way of saying that isn't that x1 is bigger than x2. Right. Oh. Imagine x1 was a boy and x2 was a girl. Then what you're saying is the girl is smaller than the boy. Another way of phrasing that isn't it the boy is bigger than the girl. So you are looking for an alternate hypothesis that looks like first one bigger than the second, which is that one. Another way of writing first bigger than second is that their difference is bigger than 0. Now here's a different one. The mean of x2 is larger than x1. Well, another way of phrasing that, I know it's the English language and it's back to front, but if that's bigger than that, then isn't that smaller than this? So x1 is smaller than x2. So mu1 is smaller than mu2. So we pick that one. No, we don't. We pick that one because it's, yeah, they match. So they're all a bunch of them. So if I do 12, it might work here. What's the difference? Oh, 12 is a 2-table one, right? So here we have 2 different populations. The first one is New England crime rate. I'm going to write that down. So X1 is New England crime rate. And the other population, X2, is a place called Rocky Mountain. And we are going to use SALT to get the mean and standard deviation of New England, which is X1, and the mean and standard deviation of X2, which is Rocky Mountain. Now this should work pretty fine, so I'm going to hit it anyway and see what we go. Boom. And when I hit SALT, we get this fella. One of these menus at the top is going to get me the mean and standard deviation of everything I want. Does anyone remember what
It's
one it
descriptive
said?
statistics to get the
That's-
stuff, and then it's inferential for the other bit.
You nailed it. So here, and I'm writing this down because I have to leave this menu, but essentially, here is the mean, here is the standard deviation of New England, X1, and here is the mean and standard deviation of X2, the Rocky Mountain. So actually, I can move this over and just do copy and paste. Darn, this is harder than it looks. Copy. What happened to them? Oh, here they are. So you type in the mean and standard deviation of New England. Which I got from that table that you no longer can see. And then the Rocky Mountain had a mean, looks like this. Oops, wrong place. The mean goes there. And the standard deviation was this number here. Okay, let me pause at that point. Are you happy with how I managed to use SALT to find mean and standard deviation in this set of data? Are you comfortable where that is and where the numbers were?
Yes.
Okay, so that ain't going to be the problem.
Yes, I didn't have a problem with that part. I got that right.
Okay, now, does this data indicate that the violent rate in the Rocky Mountain region is higher than New England? So the Rocky Mountain is higher than New England. Well, that's a funny way. Isn't that New England is less than the Rocky Mountain? You see what I'm doing there? I'm just switching them in order. But when you switch them in order in English, doesn't the relationship switch as well? So if Rocky is bigger than New England, isn't New England less than Rocky? And it's important that we get the order correct when we do our test. So New England less than Rocky. Right. So at a significance level is 0.01, which is dead easy. It's that number there. The null hypothesis is always that they're equal, so don't even think about that one. And we want the first guy, let's check that, New England, to be less than the second guy. Well, where is that? That makes it this one. Now, we have got a student T unknown standard deviation, which is that one. And then they're asking you for the sample statistic and then the p-value. And that's where the problem started. So I'm now going to go into SALT. Okay, how am I going to do this? Going to hit regression. And then it's going to be New England first, Rocky second. Let's do that again. Inferential statistics, I should do. 2 sample T. I'm going to have to zoom back and forward. 3.57. And the standard deviation was that number. That saves me screwing up in the transfer. The mean of the second place, which is Rocky, is that number, and the standard deviation of it is this number.
Professor,
Yes.
so how come we don't know the standard deviation if these are is that the population versus the sample standard deviation?
That's exactly what it is.
Because it's weird because the way the questions are worded, the other ones don't even mention standard deviation. So you're like, oh, those are the ones you don't know. But when they do mention it, it's like, well, now you don't
Well,
know.
they mention Yeah, if they mention the standard deviation, you're in a Z-scores world. If you don't know the standard, and I'm talking about standard deviation of population, that means sigma 1 and sigma 2, right? Not S1 and S2, they're big differences.
Right.
Now, are we comfortable where all these numbers came from? Right? Now, we are looking at, in this story, that mu1 is less than mu2. Do you see that? Now, how does that work in SALT? Well, the difference is always 0. So mu1, take away mu2. So if it's less than, we're looking at a less than story. Right? So mu1 is less than mu2. That's what it looks like. And then I should just generate results. And it looks like I've got a t statistic of this number. So I'll go back in and show you where that was. That's the test statistic. They're calling it a test statistic, but it's really the t value, right? It's that guy there. And now this is the p-value. Now, they don't give you a box to put that decimal in. If they did, I would just type it and put it in. But it's 0.21 roughly. Now, if you're doing 0.21, do you see it's in this range here? So you just pick the range that your p-value is in. It's in one of those, always is. In this case, it's the second dot. And they do a little picture, and it's a less than picture. I'm assuming that's 0.8. Now, the final piece is the test. Is your p-value 0.2? Is it less than that guy? And the answer is no. And when the test says no, there's two sentences that you do, one for 4 and one for 5. At the no, we fail to reject the null hypothesis and conclude the data are not statistically significant. And the one that puts those both together is that one. So when it's a no, you always choose that sentence. We fail to reject the null hypothesis and conclude that the data are not statistically significant. In other words, we can't prove anything. And then similar kind of answer, but interpret it. So we fail to reject the null hypothesis again. So it starts with the same. And we also say that there is nothing in the way of evidence. So insufficient evidence, fail to reject null. And that's how you do that question. Do you see anywhere you may have gone wrong, Joshua?
Yeah, I got it. I think what I was doing is I don't actually know what was wrong with it. Because I plugged in those values like 3 times, but
Was it
worked.
less than and you did more than, maybe?
It's very possible.
Or not equal to, or something like that. I'll
something like
just
that,
show you
yeah.
the difference. See if I change this less than to, say, not equal to. And then I say generate results. Watch this 0.21 change.
Oh, we can't see the screen.
Oh, there. There's the 0.21. Do you see it's quite different from what it was? If you did a greater than when you shouldn't have, do you see it's even worse looking?
Yeah, thank you.
So that may be where the issue was.
All right, thank you.
Are you good? Bethany, do you want me, Brittany, anybody like that? Do you want me to do another one of these questions just to go through it start to finish? Or is that good enough for you?
Can you do one more?
Sure. Right, let me just move out of that screen a bit, close off a couple of windows. Right. What the heck am I doing? closing off windows. I don't know even what windows I'm closing right now. Here we go. Yeah, well, no, it's the next question. This is the rate of hay fever people who are under 25 and the rate of hay fever of people who are over 50. And 25 in this group. Is it 25? No, it isn't. 16, that's better. There's 16 in the first group and there's only 14 in the second group, which is fine. So first thing I'm going to do is get all these numbers, and I kind of need them to do the next bit, so it's not like I can skip it. So I'm going to hit use sort and descriptive statistics, and the mean of the young people is this number. The standard deviation of the young people is this number. The mean hay fever of the older group, the standard deviation of the older group. So those are the numbers that in a few moments are going to be populated. So I'm going to put that number there, standard deviation right beside it. Then I'm going to go for the old folks. Put it here. And the standard deviation of the old folk is now here. Assume, blah, blah, blah. Here we go now. Assume that hay fever rate in each group is approximately normal. Does the data indicate that the over 50s have a lower hay fever at the 0.05 level? So the level is 0.05, and they are looking for lower. So we've got to figure out which way around that means in the story. Is the over 50 lower than the other group? Is X2 lower than X1? That means is X1 bigger than X2, which is a weird way of saying it, but never mind, it makes it that one. Aren't the young people bigger than the old people? That's just another way of paraphrasing old people less than young. Now, standard, normal, sigma unknown, student T, makes it that one. Test statistic coming up. So I'm going to have to use salt again. I'm going to go, once this is finished loading up, to inferential statistics. Pick 2 sample, and that's going to be the mean. That's going to be the standard deviation. And what, there's 16 of them. That's the mean of the other group. There's 16 of them. I believe there's 14 of them. And the standard deviation of the second group is this one. So we have to populate it, right, with all the data that's necessary. In my question, aren't we looking for the first group bigger than the second? So when we go here, greater than. Okay, so first group bigger than second, greater than the second, we're looking for greater than. It's always in terms of first group, bigger or less than or not the same as second group, right? First group, then second. So generate results, and here is the T statistic, which is pretty decent number. That looks like it's in a funny position, so let me just, yeah. If you do copy and paste, will you make sure that you don't accidentally get some spacing at the front because it might not understand that when you come to check your answer. I have a p-value of 0.018. 0.018. 0.018. 0. It's this group here. 0.18's in that range. And we're looking for a bigger than, so it'll be this fella.